Welcome, ladies and gentlemen, to this video lecture. Let us take a look at this theorem. So this theorem gives us an idea of the structure that appears in the roots of polynomials over R. So let's read this theorem. Let fx be a polynomial over R. And this over R is very important. So what does it mean? It means all its coefficients are real. So nowhere does there occur an I in any of the coefficients. So all the coefficients are real. If we have a complex root of this polynomial, then the complex conjugate of this root is also a root of this polynomial. So for example, there's a very simple example. X squared plus 1. So what are the roots of this polynomial? The roots are of course plus I and minus I. So plus I is a root, but its complex conjugate is also a root. So if you substitute it in for x here, you get 0. If you substitute minus I in for x here, you also get 0. So this happens because all our coefficients are real. So the coefficient 1 is a real number and the constant 1 is a real number. Since they are all real, then any root, any complex root of this polynomial will also have its complex conjugate be a root. And this is such a nice theorem, and the proof is also quite nice. So let us prove this. Proof. Assume, so notice here we're trying to prove if C is a root of fx, then the complex conjugate of C is also a root. So assume that C is a complex number and that it is a root of fx. Now we want to show that the complex conjugate is also a root, or in other words, when we substitute the complex conjugate into f, we get 0. So consider the following. Consider f of c bar. And now remember, where do we want to get? We want to show that this is equal to 0. Actually, before we do that, let us make f a little bit more explicit. So f is a polynomial of over R. So since f of x is a polynomial over R, there exist real numbers a0, a1, etc. up to an, so that f of x is equal to an x to the power n plus etc. plus a0. And now notice here, these are real numbers because by assumption fx is a polynomial over R. Now consider f of the complex conjugate of C. This equals an c to the power n plus an minus 1 c conjugate to the power n minus 1, etc. up to a0. But now since these an's are real numbers, this is equal to the complex conjugate of these numbers. So since the an, so a0, a1, etc. up to an are real, if we take the complex conjugate, nothing changes. So let's do that. An minus 1 complex conjugate, Cn to the power n minus 1, etc. up to a0. And now by the properties of the complex conjugate, so remember the if you remember the properties of the complex conjugate is preserved by addition and by multiplication. So by the properties of the complex conjugate, what do we have? So this is the same as the complex conjugate of, oh sorry, I forgot the exponent n there. Etc. So remember the, so what have we done here? So we take the complex conjugate, and we see here that well, the complex conjugate of a power is the same as the power of the complex conjugate. Complex conjugate preserves products. Complex conjugate preserves additions. So this then becomes, or this is equal to the complex conjugate of everything. But what is this? This is just the complex conjugate of f of c. And that is 0. This is the complex conjugate of 0, which is just 0. So therefore, c bar is a root of fx. Okay, and let me reiterate here again, this only works when the polynomial is over R. So when the coefficients are all real. Okay, and that is it for this example. I will see you in the next one.